Okay, everyone. So thanks for joining again for a Valuing Energy Data seminar. So just a little bit of housekeeping first. So as you'll notice, we're recording this meeting, so we'll be sharing that on our YouTube page after the talk. So if everyone could keep muted and hide their cameras during the talk, it just helps not to distract anything. We're going to have questions as usual, but put them in the chat. So leave them. We're going to ask questions at the end, so it doesn't sort of disrupt anything. So yeah, if everyone can keep muted, turn their cameras off, please, and we'll start with the seminar. So I'm really happy to have Dr. Hannah Bloomfield here today. I think energy and weather are such, so connected to each other. Weather is such an important component, but I think it sometimes is very difficult to sort of to value its importance sometimes and understand how much it drives so much of the energy research that we do. So I'm really happy about the talk today. So a little bit about Hannah Bloomfield. She's from my alma mater in University of Reading, a centre of sort of meteorology, but now she's just recently moved to the University of Bristol. She used to study the impacts of, she does study the impact of climate variability and climate change on national level power systems. And she specialises in modelling UK and European electricity demand and renewable generation. She's also worked on developing these tools for Mexico and multiple regions of Africa. A key outcome of her work has been to improve the accessibility of large meteorological data sets to non-specialists. So I'm very happy to introduce her now, and she's going to be talking a lot about climate and weather data for energy systems modelling. Thank you.
Perfect. Thanks, Stephen. I'll just get the screen share going. There we go.
Yeah, I can see that. That's great.
Yeah, hi, everyone. Nice to see a few familiar names in the participants, but lots of people I've never met. So this is a great opportunity for me to share some of the work that we've been doing at Reading. As Stephen said, the focus of my work is thinking about lots of different timescales of weather and climate data and how that can be used in energy system modelling. So I'm going to go through some examples today of lots of different projects we've done in the Energy Met group led by David Brayshaw, who some of you might also know. And thanks to all these people at the bottom who, mixture of energy modelers, climate scientists, who we've all collaborated together, and I think over the last 8 years I've been at Reading, made some really good progress. So let's get going. Just a bit of motivation. Why do the energy sector need to care about weather data? Well, very topical at the moment with COP coming up, but to meet the government targets, power systems are becoming increasingly weather dependent. And this results in increased variability. So we've got more wind power generation related to wind speeds, solar power, shortwave radiance and temperatures, hydropower related to river runoff, snow melt and precipitation, and also the grid itself. So could be impacted by extremes in precipitation, heat, snowfall and wind speeds. As well as this, there's our demand. So predominantly our demand is driven by temperatures. If it's cold, we use a lot of energy for heating. And in lots of other places in the world, if it's warm enough, they kick on the air conditioning. But there's also factors like wind chill and relative humidity. So weather is becoming an integral part of our power system operation, and we really need to understand the meteorological conditions associated with this new weather variability to make sure everything is kept reliable. So multiple time scales are important when you're thinking about power system operation, and with this, different kinds of meteorological products might be more appropriate. So if you're thinking operationally, trying to think about scheduling a plant or managing the grid, you might be interested in short range weather forecasts or maybe nowcasting products with satellite data. If you're interested in energy trading, you're thinking about energy contracts or potential for longer term maintenance, shutdown of nuclear, etc. You might want to look at extended range or seasonal forecasts, thinking from 1 month out to 1 year ahead. If you're just interested in the variability and the possibility of different kinds of either extreme events or conditions that could happen in a year, you might be interested in something called reanalysis, which we'll talk more about later, or maybe long simulations from present day climate runs. Or maybe if you're thinking about the future, if you want to understand the impacts of climate change on power systems, you might need climate model projections, such as the kind of things that have gone into the latest Intergovernmental Panel on Climate Change reports. And again, if you care about extreme weather, potentially you care about all of these timescales. So there's lots of different weather products. There is an abundance of weather data. Potentially, if you talked to meteorologists before saying you need some wind speed data, they could have mentioned any one of these types of products. We have observations, so these could either be from a weather station, an ocean buoy, anything standing in a field. They could be gridded observations, so data from a radar, a LiDAR, or potentially a satellite. All of these are all different types of observations. They could then be things like weather forecasts, so from various different modelling centres or run forecasts. Could be, again, this reanalysis world. So this is an optimal combination of weather forecasts with the best possible observations that we have to give us a construction of today. Or they could be these climate model simulations. But with all of these types of weather data, questions will start to emerge. Does the data need quality control? Any of you have worked with wind power data will know often this data needs heavy quality control. Observations from the weather stations are no different. Forecasts might need calibration to remove biases. Things like the climate model simulations, if they show a large amount of warming, we might be interested in, did they actually represent the current climate well? If not, we might not trust the model. Or the big question, I guess, for a lot of you is, well, from this weather data, can I actually get to a useful input that needs to go in my energy system model? And this actually leads to what we found at a conference we ran last year, that there's quite a big mismatch between the data that a climate scientist can provide versus the requirements of the people we're calling energy modelers, so anyone who's working in the energy sphere. So this graphic was made by Dr. Sophia Samos, who runs the Clinton Power Project, which I think has just finished. But I think it's a pretty good analogy for what I've experienced. A climate scientist turns up with this truck full of data, the stuff we talked about in the previous slide. But realistically, an energy modeler, this is a simplification, but in a lot of cases, you want a time series for a location or a region, which goes into a folder. So, you know, this is not exactly compatible. And a lot of the work we've done in our group is working out how we can get from this truck into the folder and make it as accessible as possible without people from the energy side having to worry about all of the steps of calibration, representativity, and just processing lots and lots of data. Because the key thing about the climate data is it's often very big. Climate model simulations are terabytes in size, and it's not very accessible to just put them on your laptop. We work on supercomputers, and yeah, not particularly accessible. So you might ask, why do you need the meteorological data? We have from, so ENSO-E or National Grid or lots of other transmission system operators, you can download time series of, you know, measured wind power generation, solar or demand. So why do we need the weather data if we've already got records? You know, we've built wind power for a bit of a while now. We're starting to get long time series. But we would argue that there's actually large trends in these measured data. So you can see from this graph here made by Grant Wilson from the University of Birmingham, which was in a blog, I think. Actually, since 2009, we've had a huge increase in the amount of wind generation on the system. And we've had a big collapse of coal, which, fantastic. But it does mean that underlying behaviour in the measured time series is not necessarily representative of today's system. So if you're looking back to, say, 2014, the wind turbines are not in the same place. There's not the same magnitude of generation. And in our group, we argue that climate variability is extremely important to account for. and we'll give some examples of how these year-to-year variations in weather can cause really big differences in power system modelling results. So in this talk, I'm going to try and answer these kind of 5 questions of why weather data can be useful. So we'll go through each one in turn. I'm going to try and keep this at quite a high level, but please do put in the chat if there are technical things I talk about which you'd like explained properly at the end, because I'm very happy to do that. I'll also share these slides with Stephen, so you can access all the links and papers and things. Everything should be open access. So yeah, what the power of having all this weather data is we can look forwards and backwards in time with different weather years in there. So for example, if we just dive into some of these questions now. Oh, not yet actually. Okay, yeah, so one of the key things we think about with this weather data is questions like on here, but the key thing I need to explain to you when using this weather data is how we get from this gridded weather data into something that we can use as a time series of energy data. So we tend to use this using either statistical or physical models. So what we've done in all the projects in the Energy Met group is we take a fixed power system setup. So the plots on there, to give an example, we can either say take the 2014 wind turbine setup for the UK, or we could look into the future. We could think about something with, say, 50 gigawatts. So we can fix a system setup and then pass many different years of weather data through a model, and then we can get many realizations of demand, wind or solar power, just with different years of weather data in it. So how we do this for the different variables, happy to go into this in more detail at the end, but our models are relatively simple because we're very focused on the weather dependence of these components. So to model electricity demand across Europe, we take 2-meter temperatures from gridded weather data sets. We aggregate them up to country level, and we turn them into things called heating degree days and cooling degree days, which they give a sense of how much our heating demand or air conditioning demand would be. These are inputs, as well as things like day of the week and national holidays, into a linear regression model from which we can get national demand. So with wind power generation, we use a physical model. So we try to get 100-meter wind speeds from these meteorological products. If they're not available, we'll take 10 meters and extrapolate them up or down. And then we pass them through a kind of wind turbine power curve. So in each grid box of our meteorological product, we put a power curve, and we can calculate wind power capacity factor at each grid box and then average them up to a national scale. A similar method is used for solar power. So the inputs here are gridded temperature and shortwave radiation. This then goes into our empirical solar model. So this is, it's an empirical model that says it's the ratio of how sunny it is compared to the maximum amount of sunshine you get at standard test conditions. And the temperature input is just to say that the solar panels get a bit less efficient as it gets hotter. So again, we take these in gridded data, aggregate them to national level, say over the UK, and then out comes solar power capacity factor. So we have lots of data available on our Reading Research Data Repository, examples of this, and we talk through the methods in quite a few papers if people are interested. So the main product we use to do this is a Reanalysis dataset. So some of you might be familiar, but if you've never heard of this before, a Reanalysis dataset is a gridded product which runs for multiple decades. So commonly they go from kind of 1980 through to the present day. So this is a numerical weather prediction model, but it's run to include past observations, and we fill in the gaps using a technique called data assimilation. So basically what it's doing is it's kind of like if the observed weather data we take from the past looks a bit like a jigsaw puzzle where you're missing pieces, because we don't have a complete observational record. The Southern Hemisphere particularly is not as well observed. But this data assimilation technique, using data forward and backwards in time and space, can estimate what these missing puzzle pieces look like, as an example here. It's a really nice YouTube video about how a reanalysis works if you're interested. So this gives us a really comprehensive gridded record of weather data for many years, and it's a great tool to use to think about climate variability and power systems. So the two main products are called ERA5. This is from the European Centre for Medium Range Weather Forecasting. And we also have MERA2, which is it's a NASA product made in America. They both give hourly gridded weather variables. So hourly is key for power system modelling. A lot of climate models looking into the future don't have this hourly component, so this is really powerful for using with energy. Okay, so let's look at some of these questions. So this summer was bad. Will that happen again next year? This question was asked to me in an email by a news reporter earlier this week, so I thought I'd put it in. To give you all some context, if you missed it, at the moment there is a big European wind drought going on. So we can use products like this Reanalysis dataset to analyse how bad this summer actually was in terms of European wind speeds. So what we've done here is we've taken this ERA5 Reanalysis product. So the World Climate Service, have produced this plot from Twitter, but it's a gridded data set, and in every grid box they've looked at the average April to September wind speeds, and they've ranked them. So the more orange it is, the kind of less windy it is. And we see over this large region over the UK, this summer was actually the least windy we've had in the whole period from 1960 through to today. So this is interesting, and potentially it can provide us some useful information when you're starting to think about extremes, because what is happening at the moment is quite uncommon. Through interacting with the meteorologists, we can unpack that a bit more. So just to give you an example of where we did unpack this a bit more in the past, so another year where we had particularly low wind was 2010. And colleagues at National Grid contacted Dirk Cannon and David Brayshaw, my colleagues, to ask about, is it likely that we'll have years with such low annual mean capacity factor? So here we've got the Dukes and National Grid data in red and green, and you can see that actually we had about 24% annual mean capacity factor in 2010, very low. Well, we can create this kind of synthetic time series of wind power generation going back all the way to 1980 using this Reanalysis data. So this is what Dirk did. He took the setup of wind turbines from 2010, calculated the wind power generation with all the years of past weather, and you get a time series that looks a bit like this. So a key point to note here is that the blue line, this kind of MERA-derived time series from the Reanalysis, in the recent period looks very similar to the National Grid data. It's a little bit high, but that's because we're modelling only physical parameters. We're not trying to do any curtailment or anything like that. So what can we point out? 2010 was anomalously low. It's like a 1 in 40 year event. So if you're worrying about if your wind turbines are productive, you can use these long-term series to estimate how long it might be before you have another year like that. Another thing we noticed was it's possible to have these very large year-to-year swings. So we see in 86 to 87, we had a very high wind year dropping down to a very low wind year. And again, this is very interesting in terms of planning, if you're interested in paying back your loans on a year-to-year basis. Okay, so next question, a thing that we're commonly asked is kind of what happens at times of peak demand. So we don't have that many years of peak demand data in the observed record from the energy data, which have a similar power system setup, so we can start to look at that. And in a study led by Phil Coker from Reading, we looked at actually planning a loss of load expectation based on all of these years of reanalysis data. So we modelled demand and we fixed it at, that looks like 2014 levels, we fixed demand. So we could adapt the model so we could incorporate demand levels at various points in time based on the data from NSOE, but we chose to fix it. So we tried to work out if we were to plan for a loss of load expectation of 3 hours per year We had 35 years of data, so that means we'll allow the system to fail for 105 hours. We looked through time at when those hours might be. So our demand is temperature dependent. So we found that actually, if you just leave it to the demand alone, a lot of the time very cold periods pop up. So we get some hours in 2009-10 where it was very cold, the black bars here. We get a lot of hours in 86 and 1990 where it was particularly cold. What we find is that thinking about just demand alone, there was over 25 hours in 86, 87 that would have missed this threshold for the loss of load expectation. But then you get many other years from sort of 2000 to 2008 where there were just no instances of going over this loss of load. So it really does make you think about this kind of variability year to year of the climate, and how just because you have a really bad year, you potentially don't need to do a full redesign of all your expectations, because climate variability and extremes play a huge role. What we also looked at is what happens if we include wind resources and see how they're contributing to the peak. So the black bars here, it's hard to see, I'm sorry, but the black bars are demand. Then if we think about demand net onshore, offshore, and a blend of renewables. So with that, we can see that including the wind resources reduces the number of multi-day events. So the wind is a lot more variable than the temperatures. And it actually spread them out quite a bit better through time. So it was interesting to know how wind clearly was contributing at times of peak demand, because the black bars are not the same as the coloured ones. Another study that's recently started to think about what happens at times of peak was led by Matt Deakin, who I think is here. So hello, Matt. You can say in the chat if I say anything wrong. But Matt was looking at, as we go on to decarbonise heat out to sort of 2025, 2030, what does that mean for the additional capacity we'll need to secure? And this is just me extracting my favourite plot from the paper, because I was involved in this because Matt wanted to think about how much different years of weather data would mean to his results. And we actually found that it makes quite a bit of difference. So what we're looking at here is the additional capacity that you would need to secure with respect to long-term climate. So if Matt compared all of the years here, so we just do a long-term mean and say that is the additional capacity we need. If Matt was to have just used 2010-11 in his analysis, that was a very cold year. We can see the mean temperature anomalies in here. But yeah, that's up to 3 gigawatts extra capacity we might have had to secure, because that's very cold, which is probably useful to plan for that, because we know that that could have happened. Whereas if you were to use, say, 13-14, this is a year that was very warm, mild, quite windy. You did not need as much extra capacity. There's lots of other stuff going on here. Matt looked at how it matters whether you add heat pumps on or not. But what's very key for us here is that weather is clearly very important. All these bars, which the only difference is the difference in the weather data that's going into them. So it's showing this of key importance. Which leads me nicely on to my next question. Does this weather even matter in the grand scheme of things? So when we started doing these kind of analysis, a lot of people did kind of say to me, well, you know, there's so much other uncertainties in how the power systems are going to develop that really meteorological variability is not a big problem for us. So this actually is something that Matt then made a very nice plot that was able to quantify for me that weather actually is quite important. So in this paper, there are lots of different types of uncertainty that Matt was looking at in terms of if you wanted to think about this additional capacity your system would need to secure. So some of them include the type of model you use. I think this is a NGESO, I think is a low duration curve framework compared to an explicit model where you explicitly model how our uptake of heat pumps would change as we go through to kind of 24, 25. So there's the choice of future energy scenario, I think taken from the National Grid Future Energy Scenarios report. There's ECR sensitivities. I think this is about how the capacity market might respond to decisions. Different heat pump scenarios, modelling is the method of modelling demand, and then there is weather. So I was very pleased to see that actually, if we just focus on this explicit model, for the years 21-22, if we think about the uncertainty here, weather is basically the largest uncertainty we have in terms of how the modelling might work. When we start to go forward, the largest uncertainty by far is this kind of heat pump scenario of how so this was all about the different shape of the heat pump profile throughout the day, which they were very different. You can see in the paper the heat pumps that we used, but weather is still a very significant uncertainty there. So when doing proper energy system modelling like Matt does, as opposed to just kind of looking at variability like I do, then yeah, definitely this is something that needs to be considered. Okay, so far I've talked a lot about reanalysis data, which is very focused on how we compare what's happening right now to what's going on in the past. So that's fine. But I think what's interesting to quite a lot of people is, can we predict these kind of events into the future? And that is something that I worked on a project called SubSeasonal to Seasonal Prediction for Energy. So this was looking at, can we forecast demand, wind and solar generation out to 4 weeks in advance? So to start with, I'm just going to give you an example of the kind of event we were looking at. So this is an event that was an extreme cold event. So UK demand forecast for the week commencing 28th of December 2009. So extreme cold. We hit a peak demand in this week, I believe. Wind turbines were starting to freeze. It was very low wind as well. So if we could anticipate an event like this in advance, it would be very useful for all types of people involved in the energy system. So we looked at sub-seasonal forecasts of this. So I'm going to show you an example here. So the observation is the purple dot where my mouse is. And then we've got the ensemble members of our forecast are given in yellow. So this is at the moment an 11-member ensemble from the ECM.WF model. So operationally, this model has 51 members, different realizations, these different ensemble members, all giving you a possible outcome that is reasonable in the future. But we were looking in hindcast mode, so we only actually had the 11 members. But anyway, you can see 3 weeks ahead, the red indicates that they're in the upper tercile. We even had 8% of members up in the extreme here, above P90. 2 weeks ahead, we had quite a lot of confidence this was going to happen. 40% of members were above the P90 threshold. And even in week 1, we were a bit less confident, but still 19% of members thought this event was very confident. So can we predict these components in advance? Well, in the project, we looked at a lot of case studies. And we were actually very lucky that in all of our case study situations, we had quite good forecasts. But this is not a comprehensive skill assessment of the model. So that's what I then went on to do. And we actually found that, yes, we can predict some of these variables in advance. So what we did is we took weather forecasts from 2 different centres. So we took them from somewhere called the Climate Data Store. That's where we were able to get seasonal forecasts, and sub-seasonal forecasts came from the S2S data archive. I can talk about those more at the end. So first we had to calibrate these forecasts. I won't talk about this in detail, but the models have biases, so we need to make sure that they represent the mean climate of the observations well, and also that the forecasts aren't too variable. So we correct the mean and variance, and then we pass them through models described earlier. So we take the gridded data, temperature data gets converted into demand, the wind speed data gets converted to the country level wind power, etc. And if you're interested, we've actually published the data sets after all this processing has been done, and we've got it into time series, and there'll be a link to that at the end. So we looked at 28 countries over Europe, and we looked at a few different measures of skill. So we've got 3 measures on this plot. So these are all forecasts of demand net wind. So we're interested in demand minus wind power generation for the countries, And we're looking at skill over the period 1996 to 2016 here. So our first metric was the anomaly correlation coefficient. So this just gives you a sense of if the forecast's anomalies are generally pointing in the right direction compared to the observations. So here we use the reanalysis as our observations to validate against, because this is our best gridded estimate of the truth. Rank probability skill score. So this tells you something about, is your forecast being in the right tercile, so upper, middle or lower. And the continuous rank probability skill score tells you something about, did you get anywhere near the right percentile in your forecast distribution? So we looked for 4 weeks, weeks 1 to 4, and you can see firstly that for our highest skill was looking at the correlation in week 1. This was very high, greater than 0.8. So 1 week ahead, we can definitely tell you across the whole of Europe information about this. So going on to week 2, the skill drops quite rapidly. And by week 3 and 4, we have, not much information left in these forecasts. But we see that if you're interested in the correlation, we can tell you a lot more than if you're interested in the more sophisticated metrics. Out to week 2, maybe week 3 for Northern and Eastern Europe, we can tell you about the tercile you might be in. But for this continuous rank probability skill score, the skill is definitely dropping out by week 3 in most parts of Europe. So what we were then interested in is, can we do better than this? This is just the skill of taking the forecast, calibrating them, and then turning them into demand, wind or solar. A big hot topic in the meteorological literature at the moment for forecasting on these kind of timescales is using weather patterns. So some of you might have heard of these weather regimes. There's a lot of talk about the North Atlantic Oscillation every time winter comes around, as that's one of the main drivers of European weather. So we have a number of weather patterns that we could define. So we looked at some traditional meteorological patterns, which are these 4 here. So they're based on large scale kind of upper atmospheric data. So we kind of look at the pressure anomalies about 5 kilometers up in the atmosphere, where everything's very smooth, and we can see areas of high and low pressure over Europe. And these have been shown before in papers by Karen van der Weijl, and Laurent Stoop, I think, is here, helpfully filled in lots of questions for me, thank you. That actually these relate kind of well to what happens in European energy systems. So our thoughts were, if we can forecast the pattern, that relates to the energy system, we might have a better forecast. Similarly, we built a new kind of patterns called targeted circulation types. So what we did is we took European energy data, so my reanalysis time series, and we did some k-means clustering on them to extract different patterns in the data. So we found that it was common that sets of Central European countries would all experience high demand at the same time, or all experience low demand at the same time. And we also saw these dipoles that Southern Europe would have low demand when Scandinavia had high, and vice versa. So we thought, well, maybe we can predict that instead and use that as a pattern. So within the project, this pattern thing wasn't totally random. We did a lot of webinars with energy traders and energy forecast users, and it showed that pattern methods are used a lot by the energy industry, but the merits of them over just this traditional method of taking a gridded weather forecast and turning it into demand, wind or solar was not really known. Been one of those things where people had decided it's good, but we didn't really know why. And it turned out when I investigated it, just using the patterns alone was not very useful. It actually did a worse job than just taking the weather forecasts and turning them into demand or wind or solar. But after a lot of messing around for about 2 years, we found out that actually the patterns, either type of patterns there, can provide windows of opportunity. So we found these kind of scenarios where if 50% or more ensemble members, so remember these are all ensemble forecasts, say ours had 11 members. So we found that if 50% agree, so 6 or more, this means that there's quite a lot of certainty in the large scale flow. So we're kind of confident of what's going on up there, which means we should have more confidence on what's going on the surface. So what we did is we extracted, there's an example here. So if this were just a 3-member ensemble, every time 2 members agree, we took those grid point forecasts and we kept them. Because we know the grid point forecasts are good quite a lot of the time. We just needed some kind of method to remove those that weren't so good. So just to show you quickly how that works, this is the grid point forecast that you've seen before for the rank probability skills score. If we are to then perform that conditioning, so because we put the condition on that we need 50% of the forecast to agree on a pattern, that means we don't have as much data in that pool. So in week 0, 94% of the forecasts have a dominant pattern. So our results look very similar. We've only thrown away kind of 6% of days, and it doesn't actually lead to a gain in skill. Whereas in week 1 or week 2, so in week 2, we can only produce a forecast for 26% of the days. But we can see that for that 26% of the days, we maintain the skill that we were seeing in week 0. So this pattern method is actually very valuable to have, but it's not going to be available all of the time to you. We can just give you these windows of increased predictability. Okay, so just finally, I'm running out of time, so I'll do this quickly, but what about climate change? So this is maybe the bit of climate data that a lot of people are most familiar with, the climate model simulations. So climate model simulations, they consistently show an increase in European near surface air temperatures. And we've just got some graphs on the side here from a paper I did recently to demonstrate this. So we used a set of models which had 6 different climate models here. Talk about them in a bit more detail in the next slide, but we've got 2 CO2 pathways, basically, an RCP 4.5, which is kind of a medium-term greenhouse gas scenario, and RCP 8.5, which is very high-end climate projection. So we see that the coloured bar shows the multi-model mean, and the dot shows each model's response. We can see temperatures here, they're consistently warming in each season, and this is averaged across over 30 European countries. So temperature, we're confident of what happens there. But with things like near surface wind speeds and irradiance, we don't have much confidence. Lots of models, these are all picked as being plausible simulations of a future climate because they all do a very good job in the present day. But lots of things happen very differently in the future. So what we wanted to understand is, how does the climate uncertainty here compare to our uncertainty in energy scenario choice when we start heading out really far into the future? So here we're thinking about 2050 rather than the near term like Matt's paper was thinking. So to do this, we use data from the ESEM demonstrator. So as I said, we've got 7 different climate models. And we've also got 5 different energy scenarios. So you're welcome to go to this demonstrator. All the data is free to download. There's an FTP, or you can point and click and make graphs around Europe. So yeah, as I said, there were 5 different energy scenarios here, and we've plotted them all on a graph here if we're just thinking about total load. So as you can see, they kind of say what they do on the tin. So 100% renewable energy scenario, fossil and nuclear, large-scale renewables. So each set of coloured lines here is all of those different climate model simulations. So what we were really surprised to find that within this data set, future power system uncertainty, once you get out past sort of 2025, is absolutely dominated by the energy policy choice. But this does not mean that climate uncertainty isn't important, because we have to make a policy choice. We can't just leave this uncertainty this wide, hopefully. And once a policy choice is made, so we picked one of these scenarios and then went on to look at the impacts of climate change. And we actually see, once you pick one, it will be actually there are actually quite clear responses. So here we're looking at the mean 2045 to 2065 change compared to 1980 to 2000. And we see that in demand, actually, there's quite a robust response to climate change, because in these simulations, demand is dependent on temperature. So summer's getting increasing demand due to our temperature increasing and more air conditioning. Whereas in winter, spring and autumn, because it's getting warmer, we need less energy for heating. So wind power, we found it was very, very sensitive to the choice of climate model we used. I put a couple of blue circles on here just to show that one climate model thought we were going to have really strong increases in European wind power, but none of the others agreed. So if you look at the coloured bars, they basically disappear. And for us, this kind of showed the danger of relying on things like multi-model mean simulations, which a lot of climate models output, kind of this ensemble mean. And potentially that masks quite a lot of useful behaviour. Solar power, we found similar things again, very sensitive to the choice of RCM, and not very sensitive to the choice of years that are being used. So one thing I just wanted to flag, I've talked about the European total, but we also looked at lots of different countries, and these responses varied a lot depending. So we're just comparing Sweden to Italy here. We see that for demand at the top, Italy's summer demand was increasing hugely, whereas in Sweden it was decreasing in every single season. So it's just interesting to see how the European picture also was masking a lot of interesting underlying behaviour. I'm going to skip this slide because I think what is probably interesting is me saying to you, this is all great. Hopefully you've enjoyed this talk or some aspects of it. Where can I get my hands on some of this data? So a list of all the currently available open access climate data for use in energy is available on the OpenMod forum. So I will post this link in the chat at the end. If you get nothing else from this, this is a great place to go have a poke around on. This list is maintained by Matteo De Felice. And this is, yeah, if you have data to contribute to this, contact him. But also we think we've got everything. So lots of different process data sets to start getting into the problem, and they have global coverage. I talked a lot about Europe today, but there's lots of stuff that you can look all over the world. Just to pick out some of the really more visual tools, if you'd rather just have a play around with some data before you commit to downloading massive swaths of it. Renewables Ninja is a fantastic tool if you're interested in wind and solar data. They use these Reanalysis data sets to do wind and solar across the whole world. You can download time series for a particular location, or you can pick a country you're interested in. Really nice resource. I think you can also choose which wind turbine you want to use to do the calculations. There's lots of flags. Ian Staffel at Imperial was involved in making this. It's really very good. ESEM, this is the tool I talked about earlier. This allows you to look at different climate change projections. You can look at the weather data, the climate models, the energy data. You can really get your hands stuck into this and think about all the different components you might need to think about. Teal tool is quite new. Again, it's a global data set that allows you to think about present climate and lots of weather variables in here. And if you're interested in the subseasonal forecasting elements I talked about, my old project, S2S4E, has a demonstrator. It's no longer being maintained, but there's lots of forecasts for past events from kind of 2018 through to 2021. I think you just have to sign up, you fill in a form, unsubscribe to some emails afterwards, and they'll, you can get a sense of this kind of skill over different European regions. And got to have a shout out for the Reading data sets that we've made. So from Research Reading, Met Energy Met, we've made lots of different data sets, Reanalysis, forecast data sets that I talked about earlier. And also, I've just been working on a project with Matt Deakin, thinking about future climate data. So we've produced a set of corrected climate change simulations, which should be up later this week, if you're interested in thinking about hourly future climate scenarios. So I'll leave my summary up because I've talked for a long time, but I'm really happy to take any questions that you've got. Thank you very much.
That was brilliant. Yeah, thank you very much. So, yeah, big virtual round of applause for the talk. Yeah, you anticipated some of the questions about data there. I guess one thing that's quite interesting to a lot of the people in the audience is a lot of licenses as well. So a lot of these aren't used for commercial, which is maybe fine if you're a bigger commercial company. But I wonder if you know, I know for instance, Mera 2 actually is one maybe that is available. but ones which sort of may be available for sort of smaller enterprises or innovators, which aren't maybe universities, which can access a lot of these things. Oh, hello. I think can everyone hear me? Or am I? Oh,
yes.
Hi, Hannah. Could you hear
yes,
that? I don't
can hear you. I could hear you. Okay.
Could you hear me, Hannah? Maybe you went
Hello,
out. Hello,
sorry.
I guess I'll just quickly repeat. You mentioned data, which is great. Academic have a lot of resources for getting that data, and obviously bigger commercial can sort of purchase that. What sort of resources are there for sort of smaller enterprises or innovators who want to get data? Because a lot have licenses which can't be used for that.
Yeah, that's a really good question. I would say the best place to probably get started is, excuse me, the Climate Data Store. If any of you have heard of this is a Copernicus product, and so the Copernicus Climate Change Service, they supply a lot of data, and I believe a lot of that can be used commercially. So all of the Era 5 data I talked about is available from there. They've also got lots of different weather forecast products. Yeah, thanks, Lauren. So the links in the chat there. So loads of different forecasting products and also future climate simulations. They're making a big push with that to try and make it useful to people rather than just a data dump. So it's got a Python API you can use to download the data. And it's got some CDO bits underneath so you can get it in a more readable format than just a GRIB file, which no one really wants.
Yeah, that's a really good point, actually. I just one more question, because you've got a lot of questions in. Lauren's has been going through there, answering a lot of them. But I guess related to that is often it's quite complicated is weather data for a layperson. Yeah. You know, like when you have temperature at 2 meters versus 10 meters, like how as a non-expert would you sort of, you know, is there resources out there for understanding it in a, you know, in a layperson, you know, way, I guess.
Yeah, it's a good point, because I feel like it's not very helpful of me to just say, oh, go read my papers, I tell you how to do it. Like that's not what you want to do, right? It's not you don't have time. But I think there are starting to be resources. So we recently ran a hackathon, an energy and climate hackathon, which I can share the link to in the chat. But we basically made sets of Jupyter notebooks which showed you how you would tackle opening climate data, how you would apply masks and do things to process it, how you can basically turn it into things you might want to use. Because the whole point of that event was, can we get more energy people interacting with climate scientists to answer useful questions? So they're starting to become resources like notebooks. Matteo De Felice that I mentioned also has some really good ones for loading large amounts of climate data. But in terms of field selection, I really think the best thing you can do is just email a climate scientist, or if you see someone on Twitter who sounds like, you know, they're from a university, they know what they're talking about. Everyone is very happy to collaborate, especially if it's stuff that they are actually quite knowledgeable about. I think that's one of the key barriers in this kind of energy meteorology field, that very few people have knowledge on both sides of both the energy and the meteorology in a lot of depth. So without talking to each other a lot, I just don't think we can make rapid progress like we need to.
That's a really good point. So yeah, I'll go through some of these questions. So it's quite a few, so maybe I'll try and be quick with them. So Peter Spark has asked about how do we solve the issue of lack of weather data from equatorial regions? I guess that's quite important for things like solar renewables as well.
Yeah, definitely. So Reanalysis can start to solve these problems because it's a global gridded record. There's a lot of work in the meteorological community at the moment working on how can we improve the quality of data over Africa, over like small islands like the Caribbean, which in some of these data sets you lose the islands because they're kind of 30-kilometer grids and they're not resolved well enough. But it's definitely an ongoing challenge. I would encourage people to look at these reanalysis style products if you want data over less well traditionally observed periods. But yeah, also speaking to scientists who work a lot on them, like some of my colleagues at Reading who work on Africa, they just know what is the best rainfall product or the best say wind speed, because they've all got their own biases, and it's again it's almost a whole field on itself to get all that information.
We've got a question from Tibby and Joseph. When you fix the power system data, how can you realistically map the upgrades on the physical system to changes in the weather or generation? I guess it's sort of about the consistencies and updates.
Yeah, no, that's a really good question. So yeah, we kind of accept, because we play the meteorologist card, and we're kind of like, we're not the experts in the power system. I personally don't know how it would evolve. I can make some guesses, but we fix it at current levels to almost hindcast what weather would have done to a current system. But in quite a lot of our work, and so Matt Deakin on the call, you might want to comment, has looked at this. Basically, you can evolve the system and include the weather data, but you have to pick fixed points. So you have to say increase demand by a certain amount, or increase the number of wind turbines, and then from that we can do another full 40-year simulation of thinking about how much difference that change in the system has made. So one of the things we've been looking at quite a lot at the moment is electrification of heat. So we've been thinking about, as we increase this temperature sensitivity, because we'll have more electric heating, what does that mean? Because at the moment, in a lot of the work I've done, I've argued, wind power is the big thing. It's so variable. We need to be able to manage the wind on the system. And what we're starting to find is actually, if you electrify heat, the temperature dependence becomes much higher, and we need to work out how to manage that too.
Good point. There's a question here about actually doing forecasts yourself, right, of weather. I guess it'd be interesting to hear, like, what can someone do themselves, with certain amounts of data. Obviously not create a complete numerical weather prediction center themselves, but I guess there might be some limitations. But what is possible, really?
So if you do want to run your own weather forecasts, I would advise people to download. So you can do this on your computer. If you've got a reasonably powerful laptop, you can download, it's called the Weather Research and Forecasting Model, WRF. So this is a model. It's like community run. Lots of academics use WRF and develop it. You can download a setup. It's not the most straightforward thing if you've never run a climate model before. But what you can basically do is download some of this reanalysis data I talked about to use as your initial condition, because you need a starting point to run it from. So you can download that, and then you can run a forecast. The thing that gets difficult if you want to run it yourself is deciding. There are lots of kind of triggers in the model, different parameterizations. So deciding how stable the atmosphere is, how you want to model the surface, how you want to do all these things. And I don't run models myself. I use the output. So even to me, that's a bit intimidating to do, but it is possible. And if you wanted to look at it, I would say that, because that model is free, anyone can run it. So that is the best entry point.
Great, WRF model. A question from Alexandra Canet says, are you looking at producing time series for energy models based on extreme value theorem? So this is the idea of then capturing sort of extremes. So I guess you showed before some extremes, but I guess this is a way of trying to put it into a model context.
Yeah, no, that's a really good question. That's something we'd really like to do. If you're interested in doing it, please get in contact with me. I think it would make a really nice kind of project for a student, because you're right, like our tails are not well sampled with what have we got, 40 years of data. There's a lot of people working currently. So there's some people at the UK Met Office, Laura Dawkins and other people there who've looked at using really large ensembles of climate data. So if you get a decent model, you can start really filling out that tail quite a bit more and getting a lot more events in it to resolve the shape. But I think, yeah, it'd be very powerful to do some extreme value theory and, really work out what's going on out there.
Your Gumbel distributions. There's quite a few questions about sort of the computational processing here, I guess. Alifia Mabin, I hope I got your name right. talking about predictions, maybe using, you did mention a little bit of machine learning, I guess, in the talk there. Is there deep learning coming into these models is one question. And I guess, you know, is there computational costs around that, and, you know, about doing those sort of things? I know the feature scalings are sort of thing going into that.
Yeah, it's a really good question. So yes, machine learning is definitely coming into this. I'm currently working with a PhD student at Oxford that's basically doing better versions of my demand models. She uses neural networks, she uses kind of quantile methods and proper machine learning rather than my multiple linear regression. And she, yeah, it's definitely coming in. Pretty much everything I've seen is coming in through Python libraries. So like Python's used a lot in meteorology for this. And any kind of verification stuff. I personally use R to do all the verification because there's some really good libraries in there. But yeah, the machine learning is coming computationally. So if you're just working on the time series data, we don't seem to be hitting any computational limits when we look at the national average. We recently ran a project where we were trying to look at on the grid, you know, doing machine learning on the gridded data rather than aggregating it up to national level, and that scaled horribly. We hit huge computational limits, even with our kind of supercomputing. So I think it does get challenging when you start to care about individual grid boxes of the model rather than like a national aggregate zone. So there's a trade-off.
I guess, yeah, we don't want them producing more carbon than will be saved by the models.
Exactly.
Niccolo Vitossi mentions, in future scenarios of high penetration of wind power, can the presence of the wind farms appreciably impact the availability of the wind resource across the country? And if it is the case, is it factored into long-term forecasts?
Can you just repeat that? Sorry, I dropped out.
Yeah. So if in future scenarios of high penetrations of wind power, can the presence of wind farms appreciably impact the availability of the wind resource across the country?
Okay, yeah, good question. From what we've seen so far, no. So we had a visitor in around 2015 who I think came and did a simulation where he filled the whole of the west coast of Ireland with wind farms just to see how much it would still, you know, reduce our generation. So obviously the wind turbines are extracting kinetic energy from the wind, and there is less. But I think the argument is so far, even with our most ambitious building scenarios out to 2050, it's not impacting. So the UK wind farms are not really impacting what is then available in the Netherlands and Germany and Central Europe. Someone can tell me if they found a study that says otherwise in the chat.
I think we've got a couple more. I guess also remember Hannah's happy to be emailed if there's any further things as well. So I'll just run through a couple more. A lot of questions. Oh yeah, what about the Jupyter notebooks? Can you share those?
Yeah, definitely.
Sounds like they'd be extremely useful.
Yeah.
And have you worked with copulars? Copulars are getting a lot of popularity right these days.
Yeah, so I have a colleague in Bern who's actually she's looking at compound demand. So she's looking at these wind drought events, but using copulars. So she's thinking about really low wind, really high demand, and then really high wind and solar. So we are working with them. It's been quite difficult to decide how to define our kind of copular events because I think what we lack, so we're doing this from a very meteorological perspective, and what we're lacking in our definitions is people from the energy system who can tell us at what point a combined event becomes important. Because we can just pick percentile boundaries and build these interesting, events. But yeah, what would be really good is to talk to people about them and say if they matter.
Yeah, I've seen a lot more in the, especially the forecasting world as well. I guess there's a few plugs for Met Office data here about a link to a data set. I guess that just my last thing really then to sort of group some of those up is, it sounds like there is some like the OSPD you were talking about, or OPSD, get it right, Open Power Systems data set you were mentioning. they're putting some data sets together. It sounds like it'd be really great to have one place where all this stuff is going. Is there ideas to do that? Is there, like, where's the first place I should go? You know, if I'm looking and you know, is there going to be more and more sort of collections of data that we would be able to find?
Yeah, no, I think that's a really good point. So the Open Power System Network did have a good crack at it. There's a lot of energy data available there, but yeah, I think the metadata is all over the place. And there's lots of different groups like me, there's people at Imperial, there's people at the Met Office. Thank you, Joanna, for the link. Yeah, there's people in Strathclyde, like all over Europe as well. There's loads of these different centres, and you basically only hear about them if we come to a talk. So there is that open mod list I mentioned, where we're trying to capture everything. So I would definitely say to people, look through the open mod list, because loads of products are on there. We all produce different things as well. So it's working out what would be useful for your scenario. But I think it would be really valuable to have a platform where there was all the energy data, all the weather data that's available, even if it's just links to, and then this stuff that sits in the middle, like these temperature indicators or whatever you might want. I think it would help people make progress a lot quicker, because I think when you enter the field, like it's a lot of spin up to learn all of this.
Yeah, and I wonder if there's the icebreaker or doing the open energy platform, whether weather data could be part of that as well, because it does seem when people release it, you know, energy data, maybe weather needs to be always accompanying a lot of this stuff. I think that was yeah, that's everything. Sorry, yeah, we overran a little bit because so many questions, so that's really great. So, and thanks for sharing the notebook. So thanks to everybody for coming. Thanks for the great questions. Thanks for Hannah, especially for a brilliant talk. You're happy to get in contact and you'll share the slides. Also, we'll have this video uploaded to our YouTube channel at the end of this. So, you know, check that out if there's anything you want to go back to. So, but other than that, thank you very much to everyone. Is the Reading one still work? Sorry, just
yeah.
Oh yeah, so
yeah.
I know you've moved on. So yeah, thanks again to everyone. So we'll see you for the next talk we have I think in about a month and a half. So we'll send that round shortly as well. So thank you to everyone.
Thank you.